In this video, we're going to talk about additional gas laws. You should already be able to identify and explain gases' properties and the force of attraction, calculate the pressure, volume, moles, and temperature of the gas using both PVT and PVNRT, memorize and utilize STP values and convert to pressure units. And by the end of this video, you're going to also be able to determine which gases diffuse the fastest, calculate partial pressures of the gas in a mixture, and calculate the density of a gas. So the questions of this video is, how do we smell certain smells from a distance where other ones don't seem to be as smelly? And why do CO2 bubbles float up to the top of the water when we exhale underwater? So Graham's Law of Diffusion says gases move from high to low concentrations, lighter gases moving faster. They have this very fancy formula that says the root mean square speed or velocity of the gas is determined by the square root of 3 times the R gas constant, the temperature, and the size. What I really want you to realize is that means that the speed of the particle is determined by how hot it is and its mass, right? So it's just mass. You don't actually have to calculate this. So what we're looking at is, if these were helium particles can go through the pinhole pretty easily, and so you have more particles on the side because they can move faster since they have a lower mass. In the second picture, with the ethylene oxide, there's the same number of particles, but less of them are getting through the pinhole because they're going to be going slower due to their higher mass, right? Even at the same temperature. If I heat one of them up, they'll move even further. So here's another example of a lab we used to do where we would wet a cotton ball with really smelly ammonia on one side and then hydrochloric on the other, and we would watch as the gas diffuses. Now, with gases, it's hard to see. You don't see anything happening until it creates this ring in the middle. The ring is made of NH4Cl, a solid, and you can see that the NH3 had to go much further than the HCl did to create that ring. And the reason why is NH3 weighs less than the HCl, so in that case it can move a lot faster, right? Alright, moving on. We can compare their speeds using the kinetic energy formula that we had seen in the previous video. So gases at the same temperature will have the same kinetic energy, so therefore their formula will become now 1/2 mv squared equals 1/2 mv squared, meaning that the kinetic energy before of the one particle is the same as the other. And the 1/2 could drop out, so you just have the mass times the velocity squared equals the mass of another substance times its velocity squared. And it creates this idea that they have to be proportional. So if you're comparing hydrogen to water vapor, the hydrogen should go faster because it weighs less than the water vapor, who should go slower because it weighs more. See how they're indirectly proportional? And here's a little graph that shows all this. So as the mass, or the square root of the mass, goes up, right, the time it takes it to move is longer. So hydrogen can move pretty quick because it weighs least. SO2 moves very slow, takes much more time to move that distance because it weighs the most. We can manipulate the equation so it looks more like this, where the mass is on the left and the volume, the velocity is on the right. So that way we can actually calculate how much faster. That way, whenever I do this calculation, I show the top mass being the more massive one because it's easier to do in my head. So water weighs 18, and hydrogen only weighs 2 because H2. So that way it's easier to do in my head. 18 divided by 2 is 9. The square root of 9 is 3. What this means is that the hydrogen will go 3 times faster than water would. So if hydrogen is going at a speed of almost 1.5, then taking a time of maybe 8 seconds, then water's going to take 3 times that amount of time in order to get to that. So how come we can smell certain perfumes from a distance while other clones only up close? If you remember in this particle diagram we saw before, this must be the cheap body sprays that we use that have weaker intermolecular forces. They have less mass, therefore they have less polarizable electrons, and they have less forces of attraction. So they're easily diffusing. Whereas this might represent the more expensive perfumes and clones that have stronger forces because they have more polarizable electrons because maybe they're more massive, and therefore they're harder to diffuse. So it kind of goes along with our idea of London dispersal force, if you remember that. Dalton's law of partial pressure says the total pressure of a simple system of gases is equal to each individual pressure. So if you had gas A at this pressure, gas B at the red pressure, gas C at the green pressure, and those number of molecules, and I smushed them all into the same container, notice the container size hasn't changed, the pressure would be the addition of all 3 gases. So in real numbers, if I had oxygen at 20, nitrogen at 78, and so on, I could add them up and make it air pressure, the air pressure being the pressure at sea level, 101.3. So it's a combination of each individual pressure in the air. Here's another example. Now we're going to bring moles into it. So if the hydrogen had a pressure of 2.9 and the helium at 7.2, the reason why helium's pressure is a little higher is because there's more moles in it, right? The total pressure is literally just added. 2.9 plus 7.2 is 10.1. But so do the moles. The moles also add 0.6 plus 1.5 is 2.1. So the pressure and the moles must be proportional. So let's think. If you think about PV and RT, PV, I would just divide by V to get P equals N over NRT over V. That means that the RT and the V, if there's the same temperature and the same volume, and the same R obviously, that would cancel out. So there's a relationship between the pressure of a gas and the moles of any gas versus the pressure total and the moles total. You could just think of it as proportions. The part of that's pressure is equal to the part that's moles. But they rearranged it on your reference table to look really fancy. They said the pressure of any gas is equal to the mole fraction, the moles of that gas divided by the total moles, times the pressure. It's the fraction of the pressure. And it's literally just a ratio. So like the pressure of the gas A is the moles of that A divided by all the moles times the total pressure. And I can do it for B or C, and the only thing that's really changing is the top numerator. So let's see the example. A mixture of gases has 4.46 moles of neon, 0.74 moles of argon, 2.15 moles of xenon. Calculate the partial pressure of each gas if the total pressure is 2. So the partial pressure is determined by the partial moles, right? 4.46 moles of neon would go on the top. The entire moles, 4.46, plus 0.74 plus 2.15 would be on the bottom, which I summed up to be 7.35. And I would say that fraction of 2 atmospheres. So neon is going to be 1.21 atmospheres. It's most of the moles, and therefore it's most of the pressure. Similarly, I can do it for argon. Argon would be the rest, the argons, 0.74, but everything else in the calculation stays the same. Since argon had a low pressure, moles, it also has a low pressure. If I wanted to do it for xenon, again, it would be the same, 2.15 divided by 7.35 times 2. Also, what I could do is instead just say the total pressure so far is 1.411 and subtract that from 2 atmospheres to find out the rest of the pressure. Here's another case of partial pressure. A 128 milliliter sample of oxygen is generated by decomposition of KClO3 collected under water at 24 degrees room temperature and 762 millimeters of mercury, so slightly above sea level. Calculate the mass obtained if the pressure of the water is 22.4 millimeters of mercury. So what we're going to do is look at how they're doing this. They're heating up a sample that's going to start to become just oxygen gas. The oxygen gas is going to go through the tube and up through into this little jar. The jar is going to create bubbles and it's going to push the water out. So originally that jar was completely filled with water. The bubbles are pushing the water out into the bigger bin. The jar now has oxygen gas in it from the decomposition of KClO3, but it also has water gas because as the water gets pushed out, the water that used to be or is still in the jar can also evaporate a little bit. So there's going to be a little bit of water in there. So what I want to think about, the reason why I think it's a partial pressure question is because we're not going to just straight go for a PV and RT and figure out how much gas is involved in moles. We're going to first say there's also water in there evaporating off of this water liquid, and therefore I have to subtract it out. So if right now the total pressure is 762 and water is taking up 22.4 of that based on the temperature it's at, I'm going to say that the pressure of the system is a subtraction of those two. Not only that, but I don't want it to be in millimeters of mercury, so I divide by 760 the pressure of millimeters of mercury at sea level. I'm multiplying by the volume it said, but remember again, the volume has to be in liters, so 0.128 liters. I'm solving for moles, the R is on the reference table, and again, Kelvin has to be the temperature unit, so 273 plus to 24 degrees Celsius. And when I calculated this, I found out that it would be 0.00511 moles, which to me means nothing. I don't know what that means. So if you wanted to, you could also change it to grams, right? It said calculate the mass, so I multiplied by 32, the mass of oxygen, and it gave me only a very small amount of gas. 0.163 grams of oxygen are evolved. We're going to do a lab like this. We might not decompose KClO3, but we will collect the gas underwater. So one question is, what happens with CO2 bubbles? Why do they float to the top, just like the oxygen floated to the top in the previous slide? I just thought the picture was cute. So let's do a small calculation to figure out what's going on. Calculate the density of CO2 at 760 millimeters of mercury, which is sea level as it rises to the top, and 27 degrees Celsius, a pretty normal outside temperature for the spring, okay, in New York. So we're going to do assume a mole of gas, just because it doesn't matter how much gas we have. If we have a mole of it, if we have a small particle of it, the density should remain the same because it's an intensive property. If we assume that, we can now do a PV and RT. The pressure is 760 millimeters of mercury, which is also 1 atmosphere. We're going to solve for the volume. If we have a mole, this is our value in the reference table, and 27 degrees Celsius has to be changed to Kelvin. When I solved it, I got 24.63 liters, which is not surprising because we're not far off from STP values, which would be 22.4. Now that I know the volume, I can calculate the density, which is always mass divided by volume. Well, where are we going to get the mass from? Remember we assumed a mole. So a mole of CO2 is 44 grams on the reference table. So we're going to take that mole grams, 44 grams, divide by the liters we just got, and we'll find a density of 1.78 grams per liter. Some people are like, hey, wait a second. Water's density is 1. Wouldn't this sink? Watch out. Water's density is 1 gram per milliliter, right? So it probably wouldn't actually go this far, but we're going to do it in the video. If you know that 1 gram per 0.001 liters is actually also the density, I just changed it from milliliters to liters, or 1,000 if you put this in your calculator, 1 divided by 0.001 is 1,000. This is the density of water in grams per liter. You have to have the same units in order for them to be compared. Now you can see that the gas is much less dense than the water, and that's why it floats to the top. At this point, you should be able to determine which gas diffuses the fastest, calculate the partial pressures of gases in a mixture, and calculate the density of a gas.